Welcome back, students of chemistry. This is a short recorded lecture on kinetic molecular theory, which is the theory about the motion of gases. Kinetic meaning moving, molecular meaning molecule, so the theory of moving molecules. You learned on day one of this unit that pressure is caused by collisions of gas particles with the sides of their containers or other objects. And we've been talking about the units of pressure. You want to put those units of standard pressure there. 1 atmosphere, 101.3 kilopascals, and 760 millimeters of mercury. You want to put those in your steel trap to help you make conversions at a later point. And the volume of a gas is how much space that gas is occupying. Please don't get confused with thinking of volume of the gas as the amount of the gas, because gases will completely fill the container they're in, no matter how small or big it is. So the amount of the gas is measured in moles. Now temperature, we studied temperature and the amount of a gas, and we learned that that temperature and pressure of a gas are directly related. And temperature is the measure of the average kinetic energy of a substance. All the particles are moving in a particular sample. They're not moving at the same speed, but the average of that speed is what we call temperature. And you learned from your lab that when you graphed your data on pressure versus temperature, that your intercept, your y-intercept, was a significant value, and it was around -300 something. So because of that, we need to adjust our temperature scale. The Celsius temperature scale does not provide us with zero pressure at 0 degrees Celsius. Zero pressure occurs when there is no movement at all. So we have to use a different temperature scale with gases. We have to use the Kelvin scale. And this is where your intercept comes into play. So on the Kelvin scale, we have a place that is 0, 0 on a pressure temperature graph. Zero movement, that would be the temperature, will cause zero pressure. So when we're dealing with gases, we're always going to convert our Celsius temperature into a Kelvin temperature simply by adding that intercept 273. So 0 degrees Celsius is -273 Kelvin. The amount of a gas is, of course, moles, and we are still going to get moles, and we are going to continue to get moles. And then later on in this unit, we are going to do something with those moles. So one of the things that we should do really quickly here is look at the relationships that you learned throughout your 3-day lab on gas relationships. And that is what we call the ideal gas law. The ideal gas law are the relationships, is the mathematical relationship between these variables. Now the word ideal means perfect. So we're talking about perfect gases here. And just like there are no ideal men or women, there are no ideal gases. But under normal conditions of temperature and pressure, these substances will follow the ideal gas law. They don't deviate much. The ideal gas law says PV equals nRT. So what we looked at in laboratory was how pressure was related. So I'm just going to rearrange this equation with pressure. And pressure is equal to nRT divided by V. N being the amount of the gas. R is something called the universal gas constant. You can get the universal gas constant in several units. The one that we're going to use is 0.0821 atmospheres times liters over moles times kelvins. And then T stands for Kelvin temperature, and V stands for volume. So if we look at our mathematical relationship, this tells us what will verify what you learned in your laboratory or what you observed. And that is that pressure is inversely proportional to volume. Notice that pressure is on the top of the fraction, volume's on the bottom. So when pressure increases, volume decreases, or when volume decreases, pressure increases. And that is an inverse relationship. You can also see mathematically that pressure and temperature are directly related. So an increase in temperature will cause an increase in pressure, and that's a direct proportion. And then pressure and the amount of the gas are also directly related. So an increase in the amount of the gas will cause an increase in pressure. We are going to use these relationships to make conversions from one condition of a gas to different conditions of a gas. So we're going to use these to solve gas law problems. And then, of course, if we don't have changing conditions, we're going to use the ideal gas law. So kinetic molecular theory. The literal interpretation we just spoke was the theory of moving molecules. And these are the observations that support this theory. We talked about diffusion in the classroom with the popcorn butter gas getting up your nose and us interpreting that as the smell of popcorn. And Brownian movement, which is observable movement of particles due to collisions. So, and that is like diffusion through water. The theory explains those observations, and it describes the differences between solids, liquids, and gases. We're going to get back to that later. We're going to focus right now on gases. But here are the major points of the kinetic molecular theory. It says that it describes an ideal gas, so it's important that you know that kinetic molecular theory describes an ideal gas, and that those ideal gases are not something that exists. The most ideal gas we have is hydrogen. It's very small, it is nonpolar, so it's moving very quickly. Okay, but the tenets of kinetic molecular theory are that gases are made of tiny particles that are far apart compared to their size. So what we say is that the volume of a gas is mostly empty space. And that's why we can take a gas and compress it and compress it and compress it, and it just gets a smaller and smaller volume. And we can't do that with liquids and solids. The second tenet of kinetic molecular theory says that gas particles are in continuous, rapid, random motion. We know that a result of that random motion is pressure. Another tenet of kinetic molecular theory is that there are no attractive forces between the particles of gases. And we know that's not true. When you did your unit on how we model molecules using valence shell electron pair repulsion theory, you were able to predict the attractive forces between particles. They were called London dispersion forces, dipole forces, and hydrogen bond attractions. And the reason that we can say that there's no attractive forces are that the molecules are moving really, really fast. And because the molecules are moving fast, any attraction that is there is overcome by the sheer velocity of the molecule. And because the gas molecules are really, really far apart from each other, they're not feeling those attractive forces or repulsive forces too much. And intermolecular forces, you know, the London dispersion and the dipole forces and the hydrogen bonding, I mean, they're just really kind of weak attractions anyway. And then the last tenet of kinetic molecular theory is that collisions between gas particles and their containers are elastic, meaning there is no loss of energy. Energy is transferred between the two particles, or energy is transferred to the container, but there is no loss of energy. And we know that in a real world, energy is always transferred somewhere else. But we're going to say that, hey, the velocity of that particle before its collision is the same as it was after the collision. Okay? So, back to temperature. We know that all gases at the same temperature have the same average kinetic energy. and that energy is proportionate to the absolute temperature, a place where there is zero movement and therefore zero pressure, and that is the Kelvin scale. And this is how we're going to convert Celsius to Kelvin when we're dealing with gases. We're going to start now to do a few problems. So if you want to, I'm going to do a different recorded segment on that. So if you want to go back through this and get your notes, that would be a great idea. And then you need to take out the paper that has a bunch of gas law problems on it. And they look like this. They have this chart, PVNT, on it. And that's how we're going to approach those problems.